Okay, so let me also thank the organizers for the invitation to be here and for organizing this wonderful workshop. I've learned a lot during the week, and it's been great. So what I'll talk about is a bit going in the opposite direction to what Sven was talking about. So Sven was talking about how to use physics to understand neural networks, and what I want to do here is to use neural networks to understand something in physics. And the problem that I'm addressing is also related to geometry, so a bit related also to GR and cosmology. Namely, I want to compute a particular type of metric which appears in string theory constructions. And this is work that I've done together with our esteemed chair here, Fabian Rühle, and who is at Northeastern, as you all know. And then with Andre Lucas, who's in Oxford, and Robin Schneider, who was my PhD student in Uppsala. Right. So the problem I'll talk about is an old problem in string theory, and it's also a problem that has been studied long from the numerical perspective. So I thought I'd just start with a slide showing a bit of work and what kind of approaches have been made. And as you see here in this slide, there are a bunch of machine learning works that has happened in the past 4 years or so. And this is really the focus of this talk. So I will not say anything about these other methods, but if you're interested in comparison, I can tell you something about that during the questions. And since this is machine learning, there are also some nice libraries that you can look at if you're interested, or some nice packages that you can look at if you're interested in playing with these tools. So if you have ever had an urge to do some string theory research and look at the hidden dimensions of our space or our universe that we live in, then you can do so now, and you can go to one of these packages and you can play around with these things and compute the metrics. The takeaway message from this talk is really very simple. So what we find is that we can use very simple neural networks that we train with a very, the most standard tools, so stochastic gradient descent, backpropagation, and this allows us to understand these tricky geometries. Now, there are two ways of understanding that. Either there is some simplification that is really underlying the geometries that we are about to discover through this research, or it's really showing the power of machine learning. And both of these possible explanations I find very, very intriguing and very interesting. And the name of the game here is really to put all of our physics knowledge or mathematics knowledge into custom loss functions that inform the network about what we wanted to do. So in a way, what I'll talk about is similar to physics-informed neural networks, PINs. I'm not sure of since I'm not a machine learning person, I'm a physicist, I'm not quite sure what the definition of a PIN is, but when I looked at the posters, which I really enjoyed, I saw lots of similarities with the kind of things that we have done and some of the posters that were talking about physics inspired in neural networks. Okay, so let me start with a motivation and a problem setup. So what is Calabi Yau space? What are these geometries that we're trying to understand? Well, they are ingredients that appear in string theory research. So string theory, to start with, for those of you who don't know it, is an attempt to quantize gravity. So it's a way that we try to understand gravitational forces in the same way as the other fundamental forces of the universe. There are various reasons why we want to do that. One is to have a more complete description of the world we live in. But there are also, and that in particular includes understanding black holes and the Big Bang at a more fundamental level than we can do with just general relativity. Now, as you know, the metric is key in general relativity. It is a tensor that tells us how to measure distances in space, and it also has information about the curvature of space. And this is the thing that Einstein's equations are determining for us. So that's the key object in general relativity. So in string theory, when what happens is that we are replacing the building blocks of our theories that are point particles in quantum field theories with strings. And this gives us a theory that includes quantum gravity, but does so in 10 dimensions. So this means that there are extra dimensions to the four space-time dimensions that we observe. So what one does, or one way to approach this, is to get rid of these extra dimensions by compactifying into a small six-dimensional space. And what six-dimensional space we choose will determine the four-dimensional physics that we observe. And in particular, the metric of the six-dimensional space will determine certain couplings and other features of the physics that we observe. So the effective field theory that would describe the cosmology and the particle physics of our universe. Now, exactly how that works is model dependent, and it's a tricky question. So this is more of a slogan rather than something that is very concrete. Now, one thing that appears to be good to do when you're selecting the six-dimensional geometry is to pick some geometry that allows a Ricci flat metric. And this is because one of the equations that we have is Einstein's equations, and we want to find a vacuum solution to that. And Calabi Yau manifolds are famously known to admit Ricci flat metrics. So this is why they have been pinpointed by string theorists as something that is interesting to look at. So the question then is whether we can construct examples and whether we can compute the metric on these examples.
We know that what you really need is something that describes one of the cosmological parameters, for example, that Ben talked about is the accelerated expansion. And so the internal space will not be Ricci flat. It needs to support a potential energy that drives all that. And so it would be very interesting if one could specialize to the Calabi Yau case. But if you look at more generic geometries, like negatively curved geometries, for example, which could also be studied using the methods that you're talking about, those start life with a really useful property, which is that they have a positive potential and they can, collaborate with other types of energy to generate the more realistic accelerated expansion. So
yeah, I completely agree with you. I think this is a very valid comment, and I completely agree. I do not think in the bottom of my heart that Calabi Yau manifolds necessarily are the solution. I think we should look at a much broader range of geometries. So this is just a motivational slide why we would care about these geometries. But I do agree, and I will also mention towards when I throughout my talk, you will see that the methods that we develop, they are more general than they need to be for Calabi Yau manifolds, and it's exactly for this reason. So the main, for those of you who are not string theorists and are not aware of this debate that has been ongoing for a long time and is still not resolved, exactly what kind of geometry we should be focusing on is a question that we are very much discussing. And there are several proposals. Now, I think the main reasons why, or one of the main reasons why we are looking at Calabi Yau manifolds is that we can construct examples. So and we can construct many examples. So that's one reason.
Great. I don't want to slow you down anymore, but let me just say for hyperbolic manifolds, not only can we construct compact examples that are explicit, we know the metrics, so you can move on to the other fields and do the kind of thing you're doing. Yeah. But it sounds like we don't disagree, and I really don't want to slow you down anymore. So thank you.
Thanks for the comment. It's a very good one. Right. So focusing on this particular type of geometries then, and just illustrating it in very simple words why we can construct many examples of these kind of geometries, even though they are compact manifolds with a lot of interesting constraints on them. The reason is that we can build examples of these manifolds from simple ambient spaces. So if you want to think about this, you can view this in the same way as we can construct, say, a sphere inside an embedding three-dimensional flat space by the equation shown here on the left. We can do similar things to construct Calabi Yau manifolds inside certain simple compact spaces and by writing down similar kinds of equations. So this way of describing geometry is algebraic geometry, and it's a very powerful tool. So this has been used in the past to construct large databases of Calabi Yau spaces. And two of the ones that we have been looking at are the CC Calabi Yaus, or the CCs, the complete intersection Calabi Yaus, and Calabi Yau manifolds that are constructed as hypersurfaces in ambient spaces that are toric. The CCs are constructed in ambient space like P4 here, which is a complex projective space. So, okay, so what are these things then? The definition of what Calabi Yau manifold is can take different forms. Here is one. So we take X to be an n-dimensional, compact, complex, and Kähler manifold with vanishing first Chern class. Now these are, so compact means that it's something small that I can make it small and I can hide it away. Complex means that I can define complex coordinates on it, and Kähler means that the metric can be determined in terms of, or is related to, a scalar potential. You take the second derivative of that scalar potential and you get the metric. Then in any given Kähler class, so that's a topological constraint, a Calabi Yau manifold admits a unique Ricci flat metric, which I will call the Calabi Yau. Now so this has been proposed as provided this topological condition here, which is that the first Chern class vanishes. So that's something that you can check using, for example, algebraic geometry for these examples. Then Calabi conjectured that this metric exists and is unique, and Yau proved that it existed. However, the proof is not constructive, so there is no analytical expression for this metric. But using these properties, that it's a Kähler manifold, and the proof by Yau for how to construct or how to show that these metrics exist, we have two more equations that we can use. So the first one is that this constraint that we are staying in the same Kähler class as some reference Kähler form means that we can write the Kähler form related to the metric that we're after in this form. So as some reference Kähler form plus some correction, where so these are derivatives, complex derivatives, holomorphic, anti-holomorphic, and phi is a function. So this is just because we constrain ourselves to be in the same Kähler class, and then we have to satisfy this equation here, which is known as a complex Monchampère equation, and this we can understand in the following way. So we are in a 6-dimensional manifold. We have differential forms here that are of two types. So the J's here, they are 2 forms, and the omegas are 3 forms. So given these forms, I can write down volume forms in 2 different ways, and these volume forms have to agree because of the topology of the Calabi Yaus. So, well, you have a unique volume form. So kappa here has to be constant on the Calabi Yau. Omega given there and the J given there are some reference forms that we can compute. So this means that the thing that we're after, which is this Calabi Yau metric, can be found by solving this equation here, the complex Monchampère equation, by plugging in this form here. So we get a second-order partial differential equation for phi. And this is the thing that we will study. So this is the problem that we're interested in. We want to find the Ricci flat Calabi Yau metric, which means solving the Monchampère equation on a Calabi Yau manifold. So how will we go about to do that? Well, what we can do if we want to solve this numerically is to sample a large set of random points on the Calabi Yau. Then we compute these forms, omega and j. We solve the Monchampère equation numerically, and we check the accuracy of the approximation after we're done. And the way we can check the accuracy of the approximation is to plug this in to the thing that we get. We plug it into the Monchampère equation and see if it's satisfied. And we can compute the Ricci scalar and see that it vanishes. Okay. So we want to do this with machine learning. So what do we need to do? Well, we need to sample our points. We want to do that. So these Calabi Yau manifolds, they have a property that they come in families, and these families are given, they are parameterized by parameters called moduli. The moduli specify how we select our complex coordinates on our manifold. So that's how we determine the complex structure, and also what these Kähler forms are. So that's related to the Kähler structure, related to volumes. So in a way that's related to the size and shape of these manifolds. So we want to, for certain moduli, we want to sample points. Then we want to feed this into a machine learning model, so a neural net that we train with certain loss functions, which will encode our constraints. And then from this, we will get a metric prediction, and we will check whether that is a good approximation. So I will talk, in this talk, I will use one of these packages that I mentioned in the beginning as to describe the implementation. And this is because this is the package that I've been working on. And it's called cymetric, and it's decomposing into two pieces. There are the point generators, and there are neural networks that give the Calabi Yau metric at a given point in moduli space. And I will, so the reason why I wanted to focus on this is to make it a bit more concrete. The other implementations that exist in the literature have slightly different choices in how to solve this, and I'd be happy to discuss that during the questions. Okay, so what do we need? Well, for the point generators, we want a random set of points on the Calabi Yau. We want to sample these with respect to a known measure, so that we can compute integrals in the end, and this is so that we can check the accuracy of our approximation. So, for example, if we want to check that the Monge-Ampere equation is satisfied, then we can compare these two different volume forms at different points in our manifold, and we can integrate that up and get a scalar measure of how well we are satisfying the equation. And in order to do that, then we need to have information of how the points where we are evaluating things are distributed over the manifold, and in particular with respect to what measure we should do this integration. So in the end, we will be interested in computing all integrals with respect to the metric that we want to learn. But this is not necessarily the metric that we sample with respect to. So we need to have compute these things with, in terms of these weighted sums. So this is what we want to get out of the point generator: a sample of points with given weights, where the weights encode what the measure is that we are sampling with. So there are algorithms for this. Yes, question at the back.
How can you compute these weights? Sorry. How can you compute these weights without already knowing the metric?
Very good question. Yes. So I was a bit quick here in the beginning. So we want the so we sample with respect to dA here. So this is we know from sampling, and then the d-vol Calabi Yau here, the Calabi Yau measure. How do we know that? Well, the reason why we know that is because of the Monge-Ampere equation here. So the left-hand side here with the Kähler forms, that is the thing that gives us the volume form of the Calabi Yau. So that's square root of metric times d x1 to dx6, if those are the coordinates. But then we know from this equation that this is related, this is exactly the same thing as kappa omega wedge omega bar. So we do know the volume form of the Calabi Yau, even if we don't know the metric already from the start. And that is because we can compute this holomorphic top form omega, and we can compute the volume form for that. So that's a very good question. Thanks for clarifying this. So actually, the first machine learning paper on Calabi Yau metrics was a supervised learning experiment to learn the volume form. And then, of course, you know what the output is, and then you can do supervised learning and compare directly. Okay, good. So to illustrate a bit the algorithms for how to find the points. So say we take a particular Calabi Yau, the simplest Calabi Yau threefold you can think of is known as the quintic. This is the picture that I showed in the beginning. So we have some quintic polynomial that takes out a hypersurface inside P4. So this algorithm for sampling points goes as follows. So we know how to sample points on P4, and that's because these complex projective spaces, they are related to spheres. So we know how to sample points on spheres, so we can use that to our advantage. So we can sample random points on P4, and then we can, so say we take 2 such points, then we can draw a line between them, and we can intersect that line with the hypersurface that we have. So that will give us 5 intersections because we have a quintic polynomial in the ambient space coordinates, and we can repeat that many times, and then we get a large sample of points on the Calabi Yau. Now, what is good about this point is that there is a mathematical theorem by Schiffman and Zeldich that tells us that these points will be distributed with respect to the Fubini-Study measure on the Calabi Yau manifold. And the Fubini-Study measure is one of these scalar forms that we can compute. It's not the only one, but it's one. And this is something that we compute by the Fubini-Study metric is one particular metric on P4, for example, and we can compute that there, and then we can pull it back to the Calabi Yau. So this sampling routine then gives us points that are sampled with respect to a known measure, which is what we want. Now this particular way of constructing the algorithm works for Calabi Yau manifolds that are given by a single hypersurface inside one complex predictive space. This is not the most general way of constructing a Calabi Yau. So if we want to go to these larger databases, so if we want to look at the CCs, then we replace the ambient space by a product of predictive spaces, and we might have more equations, homogeneous polynomial equations inside that we want to solve. So that requires tweaking the algorithm a bit. And if we go to the larger database of Calabi Yau manifolds, which are given as hypersurfaces in these toric ambient spaces that are given in this Kreuzer-Skarka list, then we need to work even more on this this algorithm for sampling it. So I don't want to go into the details here because it's not really machine learning, and it's a bit messy. But I just want to say that there are ways of doing this, and there are ways of getting the points that we want. So now we have our points, and we can pick what Calabi Yau manifold we want, which also includes picking the moduli. So that is our data that we will feed into a neural network, which will have an input layer and some hidden layers and some output layer. And then we can try to train this. And there are a couple of architectural choices that we need to make then in how to set up this network. So the first thing is what we want to predict. Do we want to predict the Calabi Yau metric directly, or do we want to predict the Kähler potential? So the output of our network, should it be a metric tensor, or should it be a scalar function? Then how do we want to encode our knowledge about the mathematics of the system? So we know that this should be a complex Kähler metric. It should be, we have the Monge-Ampere equation that we want to solve and so on. So should we encode these into the network at the get-go, or should we encode it into loss functions? So that's also a choice one can make, and different choices have been made in the literature. And then once you have made all those choices, you've set up your network, then you train it. So the loss functions that you still have, you minimize, or you run your training routine to minimize them, and then afterwards you check your performance. So as you see from this picture here, really what we are doing then is that we take this neural network, and this is the thing that will then become our approximation, either for the Calabi Yau metric or for the Kähler potential, which then gives us the Calabi Yau metric. So is this clear what it is that we're doing?
Are you going to say more about, in terms of encoding constraints, like the trade-offs between doing it in the neural network and doing it in the loss?
Yes, I will a bit. Yes, so, and if there's anything more you want you can always ask more. But so basically, I would say that if you want to be efficient, you should put as much as you can into your neural network. That's my impression. So in particular, if you are trying to learn the Kähler potential rather than the metric, that will train faster. But on the other hand, if we think about the comment that Eva made, Then there are other geometries that we might be interested in looking at after we have done all this song and dance with the Calabi Yau manifolds. And then we do not have all of these constraints already. So it's good also to keep some generality in our design in order to be able to generalize this to other settings.
And so just to be clear, in your analysis, you're going to be doing it with any constraint is always going to be a kind of soft constraint imposed by the loss. Is that
yeah, yeah, and this will become clearer. So,
thanks.
So I will have like the most the simplest kind of network and put more or less everything into the losses. Okay, and this is actually the point of this slide here. So in the package, the cymetric package, there are a couple of choices of how, so this architecture is not set from the beginning, but rather we let the user choose it. So we have, in the package, there are 5 machine learning models, and they encode these different ansatz for the metric. So one is a completely free network where the network is just predicting the metric, the full metric, and everything that goes with the metric. So this is the simplest thing you can think of, but it's also numerically a bit challenging because the metric can vary a lot. Also, when you initialize your network, it's not at all given that you will initialize it close to something that looks like a metric. So you may spend a lot of time adjusting your parameters just to get to something that is, for example, positive definite, as we want a metric to be in order to measure positive distances. And so because of that, we have all these 4 other ansatz. So one is just predicting. The prediction from the network is really, or what we get out from the network is not the full prediction, but it's a correction to this reference metric that we know, the Fubini-Studi metric. So we can do that in different ways. We can either just add something, or we can add something where we can have a multiplicative ansatz where the thing that the neural network is predicting is related to this Fubini-Studi reference metric in some particular ways. And then the last model here, the phi model, is the thing that is most similar to learning the Kähler potential in this network. As long as phi is a function, this is really learning the correction to the Kähler potential. So here we are using the fact that from the Monchampère equation, we know that the correction to the metric that we start with, the Fubini-Studi metric, should be of the form del del bar phi. So using that, we can try to learn phi directly. And then, so these different choices are then available to choose from. And we can then look at what the performance is for this most simple manifold, which is called the Fermat-Quintic. I've forgotten an I there. So here are some training results for the Calabi Yau metric package on using these different kinds of ansatz. And so what we see here are losses for the of various type, and I will soon explain what these losses are. So I just want to show this picture first to show that what is happening during training is that these losses go down. So that's the top row here. But we see that they go down with very different speed depending on the ansatz that we take. So for example, the free model is the purple one, the additive model is the orange one here, and we see that they are performing much worse than the multiplicative models and the fine model. So this is just an observation of how training works on this particular manifold. Right, so let's then go into what are the physical constraints that we have and how do we enforce them? How am I doing on time?
You have, let's see, when did you start? You started.
Okay, I think I know better than you.
I think you started about 5 minutes late.
That's true in general,
I
but
think
yes,
I have about 5 minutes. Okay. All right. So we have these loss functions. The loss functions are really important. That's where we encode the mathematical constraints. So we and we also have the question of how we train the network. So first things first, we do not know the target. We do not know the Ritchie flat metric. So we need to have a training that can deal with that. So this is not a biggie. Even when we know the target, we're really training against the loss function. So here, what we're doing here is that we are encoding the mathematical constraints as these custom loss functions, and then we train the network with respect to those. So, for example, if we want to satisfy the Monge-Ampere equation, then we want to minimize the function that is defined here, which is the Monge-Ampere loss. So this is the just another way, really, of writing the Monge-Ampere equation, and we then compute this, the norm of this, with either the square root of this or the square of this this thing here. So the determinant of the predicted metric here is really this j wedge j term for the form that we're interested in. The reason why we see the determinant and not the square root of the determinant is because this is an Hermitian manifold. So there's some magic going on there with the 6-dimensional matrix decomposing into 2 3-dimensional blocks. And this is what is given here. Kappa is the constant that we've seen from before, and omega, which omega bar is this thing that we know and that we get from sampling. Then, depending on what metric ansatz we have chosen, we need more or less other loss functions. So here's the full list of what we have. So we have the Monge-Ampere equation. We have a loss function that enforces the fact that the manifold is scalar. So scalar means that the exterior derivative of the scalar form should be 0. So this is encoded here in terms of the metric. There is a relation between the components of the scalar form and the components of the metric. So we're computing the real and imaginary part of these derivatives of the metric here, and ensuring that those are small. Then we want the metric that we're finding to be globally defined, so that we have a compact complex manifold. There are patches in which we have coordinates, and then we need these things to match well across overlaps of patches. So this is what's given here in the transition loss. So T here is the transition matrix, tells us how we go from one patch to the other and how the metric should transform as we do so. Then we have the Ritchie loss, which is given for, so this is for a scalar manifold. We have very nice, we have a simpler way of computing the Ritchie tensor than in standard differential geometry. So this is measured by the Ritchie loss here, and then we have the kind of strangest looking loss function here is to enforce that we stay in the same scalar class. So this is a topological constraint, and it's a bit hard to enforce because we need these integrals here in order to ensure it. So we cannot check that loss on a small number of points. We need to check it on a large number of points for this to make sense. So that's a bit odd. So now what's one can avoid having this kind of loss function by staying with Calabi Yau manifolds that only have one scalar class. So for example, the quintic only has one scalar class, so then it's fine. But if you want to go to the full list or the full databases of Calabi Yau manifolds, then you need to enforce something of this sort in order to be able to train. Otherwise, you would still, you would still go to decrease your loss. You would go towards maybe some Ritchie flat metric, but you don't really know how you get there because you're jumping around between scalar classes, and it becomes very difficult to understand what's happening. Right, it's the Ritchie tensor. Yeah. So this is the norm of that. Now, so as you see here, there are some of these have derivatives in them. So we need to compute those derivatives, and we use that. This package is used on is based on TensorFlow, and we use that using how we compute derivatives in TensorFlow. So using gradient tapes, but on input instead of parameters. And did I also have a comment on this? Yes, this integral here. So we compute this as a weighted sum, and in order to do that, we need a 2-step training loop to get this working. Okay, and then afterwards, we need to check that so once we have trained our network using these loss functions, we need to check that this is something that makes sense, and we do this using error measures that have been obtained or have been used in the past for these other numerical methods in order to compare across with what has been done before. So this is known as the sigma measure and the R measure. You see here the sigma measure. These things are starting to look familiar now. We have the Monge-Ampere equation again, and the Ricci measure here. It's the Ricci scalar that we are computing, and not the Ricci tensor. And we compute this as these weighted sums. We compute these integrals as weighted sums. Right, so that's the setup. So let me show you some experiments and things you can do. So and also make a bit of comments on what we can do now, which we couldn't do before. So one thing here, these are very simple examples on the quintic again, but I am comparing in the left panel here, we have the Fermat quintic again. So this varies the simplest kind of so it's the simplest Calabi Yau threefold, and at the simplest point in its complex structure moduli space where there are lots of symmetries. So if we train this phi model here, and I have a simple network with 3 hidden layers, 65 nodes wide, Galo activation function, all of the losses are turned on, but I should say that because the Ricci loss involves extra derivatives. This is turned off by default in the package, so that is not used for training. Yeah, so what's shown here is that we can train this on the simplest quintic Calabi Yau, but we can also train it on at any other place in the complex structure modular space. So we can pick some other point. Here there are no symmetries, and we still manage to train. We see that the performance, the loss. So here I'm just showing the loss, how the Monge-Ampere loss is going down on the training data. So this is not a full evaluation of what's happening in these experiments, but you can just see the trend here that it is going down, but it's in the non-symmetric case, it's starting from higher levels. It's not falling down as fast either. So training takes a bit longer, but something is happening, and it's the method is working. So this is a rather big step compared to previous numerical methods, which rely on using symmetries in order to make reasonable progress. Another thing that I've already mentioned is that we can train on quote unquote new Calabi Yau spaces. So Calabi Yau spaces that have several Kähler moduli that are more complicated, have more complicated ambient spaces. So for example, these toric ambient spaces. So here's an experiment with a bit more details here, where we are training on one of these Calabi Yau hypersurfaces in toric ambient spaces. And we check that, we see how the loss is going down, how this Kähler class loss is also going down when it's a bit more jumpy. So this is something that is important now because we have two Kähler moduli, and we need to make sure that we stay in the right Kähler class. And then we can see that the sigma measure, so if we check the Monge-Ampere equation, then for this manifold or this training experiment, it's looking pretty good. For the Ricci measure, we have some hiccups along the way. So this is evaluating, checking how closely we are to being Ricci flat during the training. So on some using the network at different points during training on some test set. And what's happening here is that there are points on the Calabi Yau very early on in the training where the metric is going negative. So something really, really funny is happening there. It's not at all what we want. The good thing is that this seems to be a transient behavior. So it's happening at the beginning of the training, but then we seem to get back to something that makes more sense. But it's certainly something worth looking into more. Okay, I'm running out of time. So I wanted to mention two papers from a bit earlier this year. So one is about how we can look at accuracy and how we can benchmark our models. So I've already said that we can use these established measures of the sigma measure and the Ricci measure to compare with other ways of computing things. There was a very nice paper by Fabian Rühle and his student earlier this year, where they are looking at making a more expansive discussion about how well these different metrics that you can compute are compare against each other, and they are doing this for the Calabi Yau, which is the cubic in P2, which is also known as the torus. So this is the manifold where we have, so it's a one-dimensional Calabi Yau, so one complex dimensional Calabi Yau. And on the torus, of course, we know what the Ritchie flat metric is. It is the flat metric, so we can compare with the exact metric there. And this is something that is shown here, but I should not really go into the details because I'm running out of time. Another thing is a discussion of how we can make sure, how we can know that we are really making an accurate prediction. So if we are training and we are getting closer and closer to something that looks Ritchie flat, we also need to make sure that we are really that the metric that we're computing is making sense. And there was a discussion about that by Per Berglund and collaborators, where they looked at how you can compute various topological quantities that using the metrics that you get from these neural networks experiments and these machine learning experiments. And what they found was that at particular points in moduli space where the manifold goes stops being a manifold, it goes singular, then you can have problems with accuracy. And they have an interesting discussion about that. And I think that's opening up for good, interesting discussions about what one should really put into the neural network from the start and what one should put into the loss functions. Okay, so let me conclude. I've told you that with simple neural networks, we can learn Ritchie flat Calabi Yau metrics, so a very non-trivial problem in differential geometry. I've said that the mathematical constraints can be encoded either in the neural network or in the loss functions. I've sort of, I'm not going into a lot of discussion about this, but there are pros and cons of these two different approaches. I've presented a bit how this is done in the CY metric package and talked a bit about how architecture and the architectural choices that we make is coupled to accuracy, performance, and generality. There are certainly many things that one would want to do with these Calabi Yau metrics. So we're only at the beginning of developing these tools. So one thing is to learn the moduli dependence, and other things is to use the metrics that we find. And but I think with that, I should really stop because I'm running out of time. So thank you very much.
Thank you very much, Magdalena. So in the meantime, I found out that we ran out of time, but we can take a question, then maybe continue over coffee.
Hey, great talk, Magdalena. Part of the, I think, context for Eva's question at the beginning is sort of like moving beyond our standard assumptions. But implicit in your talk is that in some sense, you're already doing that in a particular case, in the sense that for 40 years, string theorists have been talking about Calabi Yau manifolds. And in the case of interest, we have known zero metrics. Could you talk about some of the, sort of for the broader audience, some of the non-supersymmetric physics in the sense of moving past beyond BPS protection that you might get at in this case? What sorts of ongoing work to get at new observables is happening?
So I'm sorry, I don't think I could answer that question actually. So what ongoing work to get new observables from string theory?
What I mean is that calibration is in one-to-one correspondence with BPS protection, which is not only supersymmetric, but it's like extra supersymmetric in some sense. And by knowing the metric, there are things that we could in principle compute that we can't compute via calibration that has real physics that is, you know, in some sense only n equals 1 and sort of extra supersymmetric.
Yeah.
I guess I'm just asking you to sort of get at some of the physics that we could potentially do now that we wouldn't have been able to do without the metrics.
Right. So I think the, so there are ways that these Calabi Yau metrics enter very explicitly in the models that we like in order to compute, or in very models that have been around for a long time, in order to compute, for example, masses of the elementary particles or the fundamental fields in the construction or in the effective field theory. They compute interaction terms. They enter into interaction terms between these fields. It's something that we would need in order to study supersymmetry breaking terms as well. These metrics enter. So it's clear that having knowledge of these metrics to a reasonable precision will allow us to do more things than we have done in the past.
So thanks for the really interesting talk. Maybe you said this, but could you, given your result, your trained network, can you play the games of, like symbolic distillation or other forms of pruning to see if you can learn more about the result? Like, is there a way to simplify it?
It's a really good question, and I don't know really, but I think it's something that one should really look into. So the idea of using these, the fact that we have a neural network that gives us the metric means that we can play with this neural network and see, try to analyze it and understand what more properties of the metric.
Yeah, for example, what is the rank of W transpose W, for example? Like, how much of it matters?
Yeah. It's a super interesting question. I don't think anyone has done any work in that direction. Maybe I should look a bit at Sven and Fabian to see if I'm missing something. But yeah, it's a really interesting thing to look at.
Okay, so in the interest of time, I'd say we move further discussions to the coffee break. So let's thank Magdalena and Sven again.